In this unit, we're going to focus on integration again, but we're going to look at two fairly unrelated topics here. One is going to be calculations of center of mass and also any related idea of slicing up objects and to work with something other than pure area and volume. So that's going to be an extension of what we've seen before. Then we're going to consider a new topic, the idea of improper integrals. This is a little more abstract, and it's going to be looking at more theoretical ideas of infinities being involved in integrals and how we can handle those in a careful and well-managed way. We're going to start with our ideas of slicing, though, and we're going to start that with an example. So let's imagine we have a metal rod, and it's 2 meters long. So we've got a distance of 2 meters from here to here. And what is interesting about this rod is that it's not made up of the same material all the way through. If we look at this rod, the density is given by delta of x, which is basically 3 plus 0.5x, and the units would be kilograms per meter. So if we imagined a 1 meter of rod, how much would that weigh? That's why we'd have units of kilograms per meter for this kind of linear object. The challenge is that the density is going up. So at the left-hand edge, we're measuring x from the left-hand end. So we'll add a little scale here. X equals 0, x equals 2. At a distance of x meters from the left, the density is 3 plus 0.5x. So the density is increasing as we move to the right. Well, what does that get us? Well, can we compute the mass of this entire rod knowing the density? In principle, we should, because we have something about kilograms per meter here, and that's our density, and we have a total length, which is meters, so we should be able to multiply those out and get kilograms. And so how would we express that in terms of our quantities? The total mass would equal the density times the length. The problem with just doing that is, what's our density? It has this x in it, and so this is a changing density. If we'd said the density was 3 kilograms per meter, absolutely. 3 kilograms per meter times 2 meters would absolutely give us 6 kilograms total. But what about this increasing factor, the fact that the density is higher at the right-hand end? That pretty much rules out any simple calculation here because we'd have an x. If we plug this in, if you want to do that just for hyperbolic example here, our total density would be 3 plus 0.5x. Our length would be 2 meters, and so we'd have 6 plus x kilograms. Our bar weighs 6 plus x kilograms. But what's x? Well, x is a variable. Well, that doesn't make any sense. The bar weighs something, and it's just kilograms. It's not x kilograms. So this is a pointer that I wish it were easier, but it's not. We can't compute the total mass of this bar simply by taking the density times the length. So what are we going to do instead? Well, we have a tool in our toolkit that was perfect for this application here. What we're going to do is take our metal bar and recognize that that idea of kilograms per meter times meters works really, really well if the density is constant. So again, we have our density here times length. If we can have a constant density, say that 3 times fast, then this calculation makes perfect sense. The problem is when we try to do it for the whole rod at once, we get into trouble. But if we were to imagine a small slice, say, delta x thick, that was x meters from the left edge, then we could talk about kilograms, and that would be the mass of a slice. That's going to work because this is going to be constant, or approximately constant, on a small length. And what that would mean is that we'd use as our length of the object we're considering a length of just delta x. So we would find the mass on this thin slice of the entire rod. Of course, that means we aren't done yet. It means we have to multiply out, or add up all the slices in this particular rod at different x coordinates, but that's what integrals are for. So if the mass of a slice can be computed this way, we can now put in our density 3 plus 0.5x times delta x. That becomes the mass of one slice, and the units work out perfectly to be kilograms. With that mass then, if we want to find the total mass of the rod, then we're getting our classic Riemann sum, something times a delta x or a delta y or a delta t, this value, a function times an interval. And so the total mass would be approximately the sum of all these slices, and each slice has a well-defined mass. And we'd usually put an xi in here, so we could say, let's cut this up into a fixed number of intervals, and on each interval we'd find the density, then we multiply that density by the length to get a mass, and then we'd get the next mass and the next mass as we move from left to right. And that's all we need, as we know from experience, to then build an integral, which we'll do on the next page. Find the exact mass. Well, what we can do with the total mass now to get it exactly is do an integral of exactly that same thing that we had before, 0.5x plus 3 times dx now, because the Riemann sum that we had earlier was the sum of 3 plus 0.5 x's times delta x's, and the integral just is this sum with smaller and smaller delta x's, the limit of that. Last but not least, we would need to figure out when we start slicing and when we stop slicing, but we can do that pretty easily based on a diagram. We were told that the left-hand side was x equals 0, the whole length of the bar was 2, so the last point is x equals 2. So if we talk about all our slices from left to right, the starting point will be 0, the last slice is at x equals 2. All right, and that is our first integral with slices that isn't just about area, but it incorporates some other quantity here. Once we have that, doesn't matter where it came from, the evaluation is the same straightforward kind of calculation you've seen before. How would we integrate 3 plus 0.5x? Well, we integrate 3 gets 3x. We integrate the 0.5x, that'll be x squared over 2, add 1 to the power, divide by the new power. Once we have the antiderivative, we're going to sub in the upper and lower limits, and that's going to give us 6 plus 0.5, 2 goes into here, that'll be 4 over 2. That's the upper limit, and the lower limits are 0 and 0, plus I guess. And then we have 6 plus, that's going to be 1 by the time we're done, or 7, and last but not least, the units of that would be kilograms. We have the density, again going back to the construction of this integral, density in kilograms per meter, dx we think of as small units of distance, so meters, like so, and we would have a total mass of 7 kilograms. Now, it's worth asking, does that make any sense whatsoever? Well, I hope we can see that it does. If we imagine the bar here, we can note a couple of things. The density was 3 plus 0.5x, with x being this distance from the left edge. So at the left-hand end, the density was 3 kilograms per meter. At the upper end down here, the density was 3 plus 0.5 times 2, or 4 kilograms per meter. And we know it increases smoothly in between. It's just a linear function. So what could we do to get an estimate if we hadn't done integrals? How could we estimate the mass of this bar? Well, we could have said a low-end estimate would be to take the lowest possible density and use it all the way through. And then we can just multiply if we know that we're approximating. It would be 3 kilograms per meter times the 2 meters, or 6 kilograms. And a high estimate would be to use the highest possible density. That would be 4 kilograms per meter. Oh wait, how long is our bar? 2 meters. And that would have given us 8 kilograms. And so our exact value of 7 kilograms is eminently reasonable. So we're not just making things up, we're getting things that make sense in the context of the problem. Just as a quick recap again though, when we look at the challenge of setting up this kind of problem, what we think about is, what do we want to calculate as a total? In this case it's mass. How can we get the mass based on the information we have? We have densities and lengths. Okay, so we figure out how we're going to combine these densities and lengths. In this case it's multiplication. Then the challenge is, with the density changing, how can we find what we want, a mass, on a small slice? How do we carve up the problem so that we can get the mass of a small piece, and then we can use integral to add up the contributions of each of those pieces to get a total mass. And that's a theme you'll see through other examples in these notes as well as the practice problems.